My name is Steve Miller. I'm a math professor at Williams College, and this is the last of the coronavirus lectures on applications of quadratic equations. So these lectures are sponsored in part by the Journal of Number Theory and the Teachers of Scholars program. It's a pleasure to thank them for their support. All of these lectures are available on my homepage, linked down over here. So what we're going to do today is we're going to talk about the Fibonacci numbers. So hopefully you've seen them before. Here's a couple of nice applications of where they might occur in nature. All right, so there are many ways to define them. We actually talked about them in an earlier video, the I Love Rectangles game, which was aimed for kindergarten, but it actually has some wonderful math that's good for all ages. And you can watch that here, and the slides are also linked over here. So the standard definition of Fibonacci numbers is that we have to define the first two, f0 is 0 and f1 is 1. And then from that point onward, each Fibonacci number is the sum of the previous two. So fn plus 1 is fn plus fn minus 1. So we have a rule that tells us how to get the next one if we know the previous two. So if you need to know the previous two, how many of them do I have to give you to begin with?
Wait, what?
So if I can find out, if I know any two consecutive Fibonacci numbers, I know the next. How many Fibonacci numbers do I initially have to tell you? Two. And that's why I gave you these two. Could I tell you instead of the first, the 0th and the first, could I tell you the 4th and the 5th?
Yes.
Yeah, and then you could actually work backwards and figure out what the third is. So the sequence goes 0, 1, and what would come next?
1.
And then?
2.
And then?
3.
Yep.
5.
Yep.
8, 13, 21, 34, 55, 89, 144.
And what's next?
I can do it. It's
So,
not off the top of my head.
So if you called it 90 plus 140, that would be 234, so it's 233. So you can see each number, like 21, is the sum of the previous two, 8 plus 13. So you can go online. There's a wonderful resource called the Online Encyclopedia of Integer Sequences. It's linked over here. You can plug in your sequence, and it will tell you all the ones that have the same start as yours. And so if I plug in the Fibonacci's, here is the first couple of them. And you can see they're growing pretty quickly. So the question I would like to ask you now, and I'm going to pause the video so you can think about this, is what questions might you ask about this sequence? So I'm going to pause. All right, so we talked about a bunch of questions. So here's some that I wrote down. And some of them, you know, are there infinitely many that are prime, that are perfect squares? He asked, you know, that are perfect powers of 2, you know, 144 is 12 squared. How often does something like that happen? Perfect cubes. How fast do they grow? Could you have a right triangle where all the sides are Fibonacci numbers? Are there any interesting applications of the Fibonacci numbers? Is there a formula for each one? If I asked you to compute Fibonacci numbers, is it hard?
No.
What do you need to know to compute Fibonacci numbers?
The two before.
The two before, and all you need to know is how to do what?
Add.
Add. So if I asked you to compute the first 100 Fibonacci numbers, is it hard?
No.
Is it time consuming?
Yes.
If I asked you to calculate the first, if I gave you two consecutive Fibonacci numbers, the millionth and millionth and first, could you calculate the millionth and second?
Yes.
Would you want to?
No.
No. So the question is there a formula that would allow us to bypass these terrible calculations? Another question you might ask is, what fraction of the Fibonacci numbers are even? And in fact, some of these questions can be proven, the fraction that are even can be proven very easily. Do you have any guess from looking at this what fraction might be even?
Every other one.
So do you think it's every other one?
No. Oh, no.
Every how many? One out of every how many?
1 out of every 3.
Yeah, in fact, you can prove that 1 out of every 3 Fibonacci numbers are even.
Yeah.
So most of the questions are going to be too hard, but there are some that we can solve. And the first one is on the size of the numbers. So after the double ones, we see that the Fibonacci numbers are strictly increasing. And the question is, can we bound their growth rate? So can we get an upper bound and a lower bound? So we always like to give things good names. Why do you think we call this U of n?
Upper
and lower. And so we want to find two functions of n such that L of n is less than or equal to f of n is greater than or equal to upper n. So I'm going to pause it for a second to just let you think and see if any thoughts about what might be a good upper bound or a lower bound. So we talked a little bit about what some possibilities were. And we agreed that the beginning is a little bit annoying with the 0, 1, 1, 2. It might be easy to just start as 1, 2, 3. And some people do that. They just start with 1, 2, 3. And if you do that, then the lower bound you could easily take to just be n. The upper bound is a little bit harder. Let's talk a little bit about the upper bound. So we know the nth plus first Fibonacci number is fn plus fn minus 1. So maybe we can bound fn plus 1 in terms of just fn. And so is there a way to get rid of fn and replace fn minus 1 with something that involves only fn? So I'm going to pause so you can think about that one. So what can you replace fn minus 1 by that depends on fn and is larger, or at least as large as fn minus 1?
FN?
Yeah, it really is that easy. We know the sequence is strictly the sequence is increasing except for the double ones, but it's at least not decreasing. So we can replace fn minus 1 with fn, and this is now going to be larger. So we get fn plus 1 is less than equal to twice fn. So then the question is, how can we make this into a bound? So fn plus 1 is less than equal to twice fn. So think for a moment as to what kind of bound that might give. So let's do the calculation a bit slowly. F4, do you agree that's at most twice F3?
Yeah.
And F3, do you agree is at most twice F2?
Yeah.
Using a bound. So that's 2 squared F2. But F2 is at most twice F1. So we get 2 cubed F1.
Yeah.
If we do F5, F5 is at most twice F4.
Yeah.
But F4 we just said was at most 2 to the third times F1. So we get F5 is at most 2 to the fourth F1.
Oh, so G2 to the N
Yeah.
minus 1?
Yeah.
F1?
Yeah. And so we get Fn is at most, good job, 2 to the n minus 1 Fn. So what we've learned is it's growing at most
I
exponentially
didn't even
fast.
see that.
Well, you weren't supposed to, so I'm glad you didn't see it.
Good.
And then you can stop and you can try to figure out what would be a lower bound. The lower bound's a little bit more annoying, but I'll pause. 1. So if we try to do the lower bound, we could replace Fn with, what would give us a lower bound?
FN minus 1.
Yeah, so we replace Fn with Fn minus 1, and that makes it smaller.
Yep.
So we get Fn plus 1 is greater than or equal to twice Fn minus 1. So now we see every time the index decreases by 2, it drops by at least a factor of 2.
Yeah.
So doing the same kind of algebra, you would get F8 is at most twice F6, and just chaining this all the way down, you get at most 2 cubed F2. Similarly, F10 is at most 2 to the fourth F2, F12 is at most 2 to the fifth F2, and so after you do a little bit of algebra, you see that Fn is at least 2 to the n minus 1 over 2. And you can write this as 2 to the n halves, 2 to the minus 1 half. I'm just splitting up the exponent, right? 2 to a sum is the product of the 2's. And then we have 2 to the minus 1 half, we just keep that here, and we see we have a square root of 2 to the nth power. So we know the Fibonacci numbers satisfy the following. Root 2 to the n is at most the nth Fibonacci, and that's at most 2 to the n. So here is the conjecture. Maybe there is some special constant r, such that the nth Fibonacci number is growing like r to the n. So where do you think that r must be? What do you think might be an upper bound for that r, and what might be a lower bound for the r?
R minus 1 for the lower.
Well, what do we know about how large Fn is? It's root 2 to the n is less than equal to the nth Fibonacci is less than equal to 2 to the n.
Yeah.
We're now guessing that Fn is like r to the n. So what would be an upper bound for that r to the n? R would be at most what?
R to the N.
This has to still be true. So what do you think would be an upper bound for r?
2N? 2R to the N.
No, we have r to the n,
Yeah.
right? And what's our bound here?
2N.
2 to the n.
Yeah.
So what do you think might be a bound for r? R would be smaller than what? Or at most what?
At most R to the N minus 1.
Nope. We believe Fn is going like r to the n.
Yeah.
And Fn is between root 2 to the n and 2
Also
to the
then
n.
root 2 to the N for the lower
Well,
bound.
you gotta be careful about putting in these n's. You have r to the n is less equal to 2 to the n, right?
Yeah.
So what should r be? It's at most what?
At-
If r to the n is less than equal to 2 to the n, how large can r be? Could r be 5?
Yeah.
So you can have 5 to the n is less than equal to 2 to the n.
Oh no. So it has to be less than 2.
Has to be less than equal to 2. And let's look in the other direction. Root
And it
2
has
to
to
the n.
be like more than like 1 point.
So root 2 to the
Two?
n is 1.414 roughly.
Yeah.
So root 2 to the n is less than equal to r to the n. So what's the smallest r could be? Don't give me the decimal, just tell me the number.
Root 2.
Root 2. So R would have to live between root 2 and 2. So by doing that simple calculation for the upper and lower bounds, it's telling us, no, it's not unreasonable to guess something like this. And so we can go through now, and we're going to see now the quadratic formula emerging. Let's just guess that Fn is R to the n. So then Fn plus 1 would be R to the n plus 1, Fn minus 1 would be R to the n minus 1, and we substitute into our relation. So we get R to the n plus 1 is R to the n plus R to the n minus 1. We subtract everything. And notice how everybody is a multiple of R to the n minus 1. We pull that out, and then we have, this was an R to the n plus 1. We pull out an R to the n minus 1. It's left with an R squared. Because R squared times R to the n plus 1 is R to the n plus 1.
Yeah.
Similarly, for an R to the n, that's going to give us an R, and this is a 1.
Yeah.
So what is the only way a product could be equal to 0?
If R is 0.
So one way is for R to be 0, that's, or
n minus 1 be 0. For n to be 1, so n minus 1.
no, because if n is 1,
Oh,
that's
no,
just,
then Andrew.
how can a product be 0? If I give you two numbers that multiply to
If
0.
Well, if R squared is, if R is 1. Wait, no.
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 So tell me, when can a product of two numbers be 0? What must be true for a product to vanish? If x times y equals 0, what do you know?
What, either x or y is 0.
Either x or y is 0. So if I tell you r to the n minus 1 times r squared minus r minus 1 equals 0, you know that either
R n minus 1
is 0,
or R squared is 0, or R is 0.
or what is 0? So r to the n minus 1 is 0, or what else is 0?
Like R squared.
Just r squared?
No, R squared minus R minus 1.
Right, because this product is equal to 0. The only way the product can be equal to 0 is either the first piece is 0, or the second piece is 0, or both.
Yeah.
Well, r equals 0 is absurd. That would just give you each Fibonacci number is just a 0. So if this is going to be true, r would have to solve r squared minus r minus 1. How do we solve that?
R squared minus R minus 1.
Yeah, how would we solve for that equals 0? What would we use?
The quadratic.
The quadratic formula. So we know if you give me f of x is ax squared plus bx plus c, the roots are just negative b plus or minus the square root of b squared minus 4ac over 2a. So for us, we're not using x as a variable. What are we using as our variable?
R.
R. So what would a be, what would b be, and what would c be? A would be
1.
A would be 1. What would b equal?
Negative 1.
And what would c be?
Negative 1.
So we would get those three values, and then you would plug those values into here. So pause so you can try and see what you. All right, so we just did the algebra here, and we got the following one. Oops, this should be a plus or minus. Negative 1 squared minus 4 times 1 times negative 1, all over 2. And we get the two roots are going to be 1 plus root 5 over 2, or 1 minus root 5 over 2. Okay, and so now, if we try that, we saw that R must satisfy this equation. It was a quadratic. We know how to solve quadratics. And we found two roots that worked. One with a plus sign, one with a minus sign. Now here's a little bit advanced, but it's going to allow us to review some stuff you're doing in Algebra 1. If R to the n works, so does a times R to the n for any constant. And the reason is, if R satisfies this, if I multiply everything by 5, it's still going to be true, because I'll multiply the left-hand side by 5 and the right-hand side by 5. So you can just do the algebra and show that that works. Another thing you can show is if R1 and R2 both work, so if we raise these to the nth power, their solutions, so does this linear combination, A1, R1 to the n plus A2, R2 to the n. Any constants A1 and A2. And you can just go through and say, if R1 to the n satisfies this relation, and R2 to the n satisfies this relation, when you plug this in, it still satisfies. So here's the question. Can we find constants A1 and A2 such that this relationship works, and that gives us the nth Fibonacci number? So how would we do that? So I'm going to pause and give you a chance to think about this. And the hint I'll give you is, I'll ask my assistant, how many conditions, how many numbers do I need to specify for the Fibonacci relationship? So I gave you the relationship. In order to know all the numbers uniquely, how many terms do I have to start you out with?
2.
2. So by using 2 terms, everything else follows. So what we're going to do is we're going to take f0 equals 0 and f1 equals 1 and use those to find the two unknowns. We have two unknowns, so two equations can do it. And again, we could have chosen any value of n we want, but by choosing the smallest values of n, it's going to make things as easy as possible. So when we put in n equals 0, anything to the 0th power is
0.
Is 1.
Because
So we get 0 is a1 plus a2. That's taking n equals 0. And then when we take n equals 1, we get 1 is a1, 1 plus root 5 over 2, plus a2, 1 minus root 5 over 2. And on the next page, we'll do the algebra and see we get a1 equals minus a2 is equal to, whoops, it should be a minus, it's just equal to 1 over root 5. And so this leaves us with the wonderful Fibonacci formula. And I always find this formula amazing for the following. Imagine that you get beaten up by a Fibonacci number and the police form a lineup. And they have a bunch of numbers there and they want you to identify who did it. What do you know about the Fibonacci numbers? What type of numbers are they?
They're positive.
Okay, more than just positive. What kind of numbers?
They're plus, like,
Yeah, well, then you have numbers like 1, 2, 3, 5, 8, 13. What kind of numbers are these?
counting numbers.
Counting numbers, whole numbers,
Yeah.
integers. They're not fractions, they're not irrational. Look at this. We've got division by 2, we've got square roots of 5. And yet somehow at the end of the day, it ends up as an integer. Amazing. So here's how you would solve the system of equations, which I know is something that's done in Algebra 1. So from the first equation, if 0 equals a1 plus a2, we could just get that a2 is equal to minus a1. And then we could substitute that into the second equation. And then you get 1 is a1 times this, minus a1 times 1 minus root 5 over 2. So we just multiply everything out. And you see the a1 times the half cancels with the a1 times a half. The a1 root 5 over 2 reinforces the a1 root 5 over 2. We get a1, 2 root 5 over 2 are just a1 root 5. So we get a1 root 5 is 1, so a1 equals 1 over root 5. So this is a value of learning how to solve systems of equations. We were able to use this to find the Fibonacci's. And again, if you don't want to solve for a2 in terms of a1, you could have just subtracted this equation from this one. So this wonderful formula allows us to jump to any Fibonacci numbers without computing earlier ones. But it means we have to compute stuff like 1 plus root 5 over 2 to the n. So how hard is it to do that? What would you use to compute 1 plus root 5 over 2 to the n? I'll pause so you can think about this. So when we want to compute this, the bottom 2 to the n, that's not so bad. But the 1 plus root 5 to the n, how do we compute that? Well, that's actually, we did that in an earlier lecture. That's Pascal's triangle. So we would just use Pascal's triangle to expand things out. And one thing that's really nice is things are going to be these binomial coefficients, Pascal triangle numbers, times 1 to a power and root 5 to a power. What's root 5 squared?
Root 5.
Yeah, root 5 squared.
Root 5.
Root 5 squared. What is root 5 times root 5?
Wouldn't it just be 5?
Would it just be 5?
Like I said. Like
oh, no, I thought you said root 5.
No, I said
Okay.
5.
Okay.
Like 5
okay.
times.
I didn't hear the 5. I heard the root 5. What about root 5 cubed?
5 times root 5.
Root 5 to the 4th.
25.
Root 5 to the 5th.
25 times root 5.
Root 5 to the 6th.
125.
So do you see how it's alternating?
Yeah.
So whenever you have root 5 to an even power, it's going to be an integer, and root 5 to an odd power will be an integer times root 5. So it's actually going to be pretty easy to compute this. So the last thing I want to just mention is the growth rate. So if you look at this, 1 plus root 5 over 2 is about 1.68. 1 minus root 5 over 2 is about negative 0.618. So this number is greater than 1 in absolute value. This number is less than 1 in absolute value. If you have a number that's less than 1 in absolute value, and you raise it to higher and higher powers, what does it go to?
A higher number.
So you have like a half, and you keep raising it to higher power.
It goes down.
It goes down to what?
Like 0.
To 0. If you have a number that's greater than 1, what happens is you keep taking
It goes up.
It goes up. So when you look at this, which number do you think is going to matter? Which factor do you think is going to matter when n is large? The first term or the second term?
First term?
Yeah, what is the second term going to?
0.
0. So the nth Fibonacci number is approximately 1 over root 5, 1 plus root 5 over 2 to the n. And so they often call this number 1 plus root 5 over 2 the golden mean. has a lot of wonderful properties. And so, as for that, because this is greater than 1 in absolute value, this term dominates.
Is the golden mean your favorite number because it's the reciprocal of its own inverse?
Yes, in fact, the golden mean is the reciprocal of its own inverse, and that is why I love it so much. So here is a few Fibonacci numbers. Here's the 100th Fibonacci. Here's the 1000th Fibonacci. And making the font a little bit smaller, here's the 10,000th Fibonacci.
What's the millionth?
The millionth would overflow my screen, even on a super small font. So the question is, can you get
How
a
many
sense?
digits is that?
So that's a great question. And I can calculate approximately how many digits that is. All right, so I will pause this for a moment. This is actually a typo. This should be the 10,000th Fibonacci, not the 100,000th Fibonacci. And it's about 2,000 digits. So the last thing I wanted to talk about is I plotted a ratio of Fibonacci numbers and the golden mean. The golden mean is 1 plus root 5 over 2, about 1.618. And so I looked at the ratio of Fn plus 1 over Fn. So 2 over 1 is 2, 3 over 2 is 1.5, 5 over 3 is 1.66, 8 over 5 is 1.6. Do you see how they're converging to about 1.618?
Yeah.
What if I have them in 2 different colors?
So it makes it easier to see.
Look at the behavior of the 2 different colors. What do you notice about the orange ones? 2, 1.666, 1.625, 1.619, 1.61818, 1.61805. They're getting smaller. What do you notice about the blue numbers? They're getting bigger. So it looks like the even ratios are converging from above and falling downward, and the odds are converging from above, from below and rising up. That seems to be holding for every single term. Do you think this holds forever?
No.
Or you think this is a function of I've only gone up to 20?
I think it might hold.
So we can actually prove that it holds forever. Let's look at this formula. Look at how we are subtracting this little bit from the Fibonacci's. If n is positive, if n is even, what do you know about the square of any non-zero number?
Any square of a non-zero number?
Yeah.
It's positive.
It's positive. So if n is even, then if I approximate the Fibonacci number by this, I'm actually a little bit too high.
Unless it's not.
But I is not a real number.
Yes, sir.
So if n is odd, and this is negative, what is it to an odd power?
Negative.
Negative. So then if I approximate Fn by this, I'm actually a little bit off. I'm a little bit too small. And so I should have paused the video, but it's getting late. So that's really what's going on, is by looking at it, this over here is going to be alternating between positive and negative. And that's what's responsible for the fluctuations. So the last lecture in this series is actually already online from a class I did before, which we will post later. It's on applications of Fibonacci numbers and their generalizations to roulette. As always, we hope you enjoyed these lectures. Be responsible, have fun, do math. Take care.